sorry. So the next talk is on Virtual Observatory and its tools, and it is by Hasan. So we'll start on that, and please put your questions in the chat window or on YouTube chat. Yeah. Okay. Thank you.
Hello, welcome back to the next session. So I'll be talking to you on virtual observatory and tools. So basically, so the plan of my talk is to give an introduction to virtual observatory and its tools and its integration with the astrophysical data system. So basically, we would like to introduce the participants to various astronomical data sets which are available. We'll try to help them install the required software to analyze this data. We'll show them how to access this data and then to use these tools which are freely available for everyone to do science with. Software like Aladdin, DS9, ESA Sky, TopCat, and so on. We'll also have hands-on sessions on the use of the viewer tools and the archival data as we proceed ahead in this or the next session. The minimum requirements is some basic computer knowledge. People should be able to handle essentially a laptop or some computer, nothing much. And most of these tools are Java based, so it's independent of which operating system you're using. You may be using Windows, Linux, or Mac. And we would encourage, if people have their laptops with them at different stages where you are required to download something and install, you may do that. Yeah, and one thing essential which is required is a good internet facility. And those who are connected to us online, they already have it. And those who are in the call right here, they also provided with it. So I think this is good enough for start. So here's the image of our galaxy, the Milky Way. And it's the same object which we see, but in three different wavelengths. This is the optical image. We discussed what wavelength is, right? So we are looking at the same object in different wavelengths. One is in the optical, one is in the infrared, and the third is in the radio. And what is this? This is the galaxy in which we live, the Milky Way Galaxy. Okay. And if you see optical, it looks as though there are some patches here. These are stars which are shining, which appear white. And in between, it appears that there are some gaps here, showing that there is no star, right? It appears there is nothing there. But when you look in infrared, you see that there are no gaps at all. There is something there. There is matter. But we don't see it in optical because it's not hot enough to be visible. But infrared, which can detect even colder material, it does detect it. So there's a uniform distribution and there are no patches or holes. There can be huge, big, dark clouds where there may not be any stars, or there may be stars which are obscured in these huge dark clouds. And this is the radio continuum, which basically shows the distribution of hydrogen, neutral hydrogen in the galaxy. And you can see that it is extending much beyond the optical extent. So it is truncated here, but it would, if you see the whole map, you will see that it extends much further. And you can see that there is a thickening of the disk here. There are thin parts and thick parts there, and so on, right? So the cartoon on top gives a story of these blindfolded men, 5 of them. So they are blindfolded. They cannot see. So one person touches the back, the tail of the elephant and says, "Oh, elephant is like a rope." One person touches the leg and says, "Oh, elephant is like a trunk, a tree." One says, "Oh, it's like a wall who is touching." One touches the ear and says, "Elephant is like a fan." And the fifth one is managed to catch hold of the trunk and says, "Oh, it's like a snake." So everyone is correct in his own right, but it's not the right picture. To get the right picture, you have to observe uh, each aspect of it. So when we use when we use multi-wavelength observations, we get the right picture of an object, right? Otherwise, we would see only one set of phenomena which is going on, you'll get a wrong impression of it. Similarly, here are the images of the Andromeda galaxy, which is the next closest major galaxy close to Milky Way. And this is what it looks like in the visible light, in the optical one. This is in infrared, this is in radio, ultraviolet, and in X-ray. Okay, so it's become essential to understand the phenomena. If you understand a particular object, or a particular galaxy, or a cluster, or a region in space, it's better you observe it in various wavebands, and that's what is happening now. And hence we are living in, so now we are living in this multi-wavelength astronomy period. There are various ground-based and space-based telescopes, and they are observing the skies in gamma rays, in X-rays, in ultraviolet, optical, infrared, radio, and so on and so forth. So there's tremendous amount of data coming in from various observatories, and most of it is we get wasted. There's so much of data which comes in. People who observe, for each observatory, they have a system of allotting time. So you have to write a schedule. You have to say what do you want to observe and what's your purpose. And if there is a good scientific basis, then you are given time to observe those objects. So there are many observatories, like in India, we have one in Hanley, we have one in Himachal area in Devasthal. We have one in down in South Kavalur and so on. And similarly, all over the world, Japan has, US has, Hawaii and Australia, and innumerable observatories. Apart from this, there are many sky-based observatories. They are satellites, which in the morning we heard from Dr. Gyana Gandhi. And there is one dedicated satellite sent by Indian community, which is called Astrosat, and it observes objects in X-rays in multi-wavelength, right? So there's tremendous amount of data which comes in, and after some time, this data is made available for everyone to use. So there's a proprietary time. If you write a proposal and it is accepted from Hubble Space Telescope or whichever telescope, for a certain period of time, the data remains only with you, the principal investigator, and after a certain period, the period varies from observatory to observatory and the rules and regulations. After that, this data is put on the internet and made available for anyone to download free of cost and analyze. So this whole exercise which we have been doing for the last 2-3 years is telling students, people who are interested, where to get this data from and how to observe. So in this regard, so that there should be no confusion and wastage of time, uh, this Virtual Observatories Alliance was started, where they defined certain protocols and rules and decided that the data should be shared in certain formats and in certain way. And they also developed certain tools, virtual observatory tools, which they make it available free of cost for everyone to use and to do science with it. So there was a time in astronomy was there was not much of observations in astronomy. People had to look through a telescope, and what they saw, they used to draw and do everything. Then there were times when they started putting photographic plates and image it. But one image was an image. And then the sophistication increased, and now we have CCDs, which we heard about. And each snapshot, you can have multiple snapshots of the same thing in different wavebands, and all this data is available. So astronomy has grown from a data poor to a very data rich science. And astronomical data is leading to petabytes of data, and it is increasing tremendously with every year with improving technology and new observatories and systems coming in. So in the morning session, Dr. Sushant Kunar also spoke about the amount of data which is collected by SKA, the square kilometer array, and it is much, much more than even the Facebook data is, right? So it's amounting to petabytes of data. And so astronomy has evolved from this data poor, hypothesis driven science to a very data rich science. Just to give you a glimpse of the amount of data which we are getting, we have this DPOS, the Palomar Digital Sky Survey, which is 3 terabytes of data. The 2MAS, the 2 micron All Sky Survey, 10 terabytes. Galax is 30 terabytes. And if you go down, this VRO is 14 terabytes per day and 50 petabytes per year. So, and this LSST, the Large Synoptic Survey Telescope, is expected to collect 200 petabytes of data. And this SK, which we spoke about in the morning, is expected to get 400 petabytes per year, right? So imagine what's happening. And this is the timeline of data access and interoperability. 1960s, the beginning of computer connectivity. We had the ARPANET and internet. In 1970s, the email started and ARPANET standards of encoding messages were established. 1980s, we have this World Wide Web at CERN. Global hyperlink information systems were built. 1990s, web browsers, CERN and Slack were put in place, and so on. And in coming down till 2010s, the growth has been tremendous in various areas, and the interoperability has put in place, where the data is being shared in a fair way. Yeah, it's everybody which has the equal right over the data, and it is not the proprietary of some individuals to hold the data and hold science and its knowledge only to them, but it has to be distributed fairly. It should be accessible, and people should be able to find it. And let's proceed further and see how these developments have grown into IVOA, and the International Astronomical Union and the United Nations have played a role in defining these fair standards in which data would be distributed among researchers, and the interoperability and the use of this data in peaceful ways. That is the underlying thing, that the data given is for science, and to be used for peaceful purposes only. The Open Universal UN initiative, which is under approval, will be based on the IVOA standards and collaborations with the IVOA. So what is this virtual observatory? A multi-wavelength digital sky that can be searched, visualized, and analyzed in new and innovative ways. Right? This is what the basic definition of the virtual observatory is. Virtual itself indicates it's not real, right? So it's a consortium of various observatories, and virtually this data is going to be a place where you can search it, access it. You'll have tools to visualize this data, make sense of it, make plots, make patterns, look at images, right? So the data comes not only as astronomical images, but also as catalogs and time series analysis, like the things which we heard Dr. Priya speak about in the morning. And to make available for people to analyze and their own innovative ways and to make science out of it. So what is this virtual observatory? Each data center archive with different file structures. They have these metadata and table organization. The data is there, but it takes work to access it, especially in several data sets are used together. So they decided that the data should be given in a file format which is called the FITS format, which was mentioned in the morning. The FITS format is a standard one where you not only have images, but you also have other information which comes along with it, which says what was the exposure time, what were the filters used, which observatory was used, at what time, what was it used, and so on and so forth. Yeah. So as we proceed ahead, we'll have certain, we'll download some data from net and we'll see how these FITS files appear and how do you read it, right? So normal tools of seeing photographs which you take on cameras are not suitable for this. There's specific software which you have to use, and it's easily downloadable. So the framework is for these data archives to organize access to the astronomy community, which are holding data in common agreed standards, and to share the data structure according to some defined data models, and software providers to create some compatible ways of analyzing this data out as visualizing tools and various interfaces. And the data centers to provide a cooperating data service. So this IVOA is composed of, you see, all these countries, Australia, Canada, India is also there. This is BO India. Yeah, and all these countries. There are 21 IVOA projects right now. And it is essentially to facilitate the international coordination and collaboration necessary for development and deployment of tools, systems, organizational structures necessary to enable the international utilization of astronomical archives as integrated and interoperable virtual observatory, right? So we have GAVO, HVO, and Japan, GBO, right? There are all these countries which have come together and have developed various, each one has looked after a different data center, or they have created repositories and mirror sites in the countries, making it accessible for those regions, and also have participated in building different tools. So BO India too has played with persistent technologies, developed tools. It was under IUCA Pune for a long time. So the IVOA organizational chart goes this way. You have the media groups, you have the executive committees, technical coordination groups, committees on science proprietaries and standards, with defined standards and protocols and processes committee and so on. And then you have the working groups where they say what applications could people work on, or what are the data access layers, that what layers, which group should be given access to data, about the data registry and so on and so forth. And then you have the interested group where they either they curate the data, they archive it or so on, or they use the data for educational purposes, or they build theories over it to time domain operations. They work for knowledge development and so on. And there are some which work on solar system aspects, and right. So there are these interested groups, and this is how it functions. So, like you, to visualize, there is something called DS9, which we can download and see this data. There is TopCat, which is a very good Java-based application, which allows you to look at tables and make plots. And in fact, these all are interconnected. You can use TopCat to do a cone search and get data from the net, to analyze it, to make graphs, to visualize the whole thing, right? So look at the catalog. And then you have these programming languages. For example, you have Python, which is getting very popular now. And there are various modules and libraries. In Python, you have AstroPy, and which is specifically designed for doing science with Python on astronomy data sets and so on. And then all this, it's important that we don't blindly do it. Should not use it as a black box. It's always better to use these tools, take some data which you know and understand, and see whether it's doing what you expect it to. For example, suppose you make a 2-column data set and you have a linear equation, and you plot it and you have to try to get it. You deviate a few points and try to put a correlation line, regression line, and see whether you are getting the right fit or not, right? So initially just play around with these and don't use it blindly. Don't use it as a black box. Then you have this metadata, which has the descriptive information about the data. It also, the FITS format, which we are talking about, it also gives you information about what telescope that image was taken by, what was the exposure time, the bad pixel mask, and various other details, the time of the observation data. So we'll be seeing that. And you can also do simulations. You can simulate using these things to artificially construct data, run these tools, and you match it up with the actual ones to see whether your theory and your observations are going together. And then you have this spectral data too, where you can do time series analysis. And then, so you have these VO data, which are kept in various sites. You can use TopCat, access the data through TopCat, analyze it. Then you can, similarly, you can take data from Chandra, you can take it from different sources, and you can overlay those two things. You can take tables coming from different sources, match the tables and various things. You have this DS9 and Aladdin, where you can visualize it and you can do some image processing, image analysis, the setting of contours, various things, right? And you have the Sherpa. I think there'll be sessions on this too, where you have you'll be installing Chow tomorrow and using that, right? And then if we have time, or we'll get you to this Python scripting, where we introduce you to AstroPy, how Python can be actually used for accessing data, analyzing it, and doing science with it. And these are all interoperable. Your data can flow from one to the other zone, and we'll have a look at that. You have this Strasbourg Astronomical Data Center, CDS, where you have a host of catalogs which are kept there. And if we just do, I'll just show you. Anyway, or we'll just go through this and then have a look at it. Instead of coming out of the presentation and going back. After that, we'll open a browser and search for these things. And we have Simbad, where you have astronomical databases. So as of on 11/12/2021, it had 12,951. Yeah, 12,950,737 objects, right? And yeah, so there's enormous amount of data which is available. We have these Vizier services, which provides the most complete library of published astronomical catalogs, tables, and associated data. And we can access it just with a click of it. You have these query forms here, and you can give the data name, and you will get to know where are the data available, what work has been done, all that would be got through this. Then we have this Aladdin, which helps you visualize the data. You can see images on this, and you can stack up. It has many frames. You can stack up various frames. So you have the optical image. Over that, you can overlay the X-ray sources, and over that you can put the infrared one, and you can make a composite one and see. Yeah, so it's a beautiful tool, and there are various tools here with which you can do various kind of activities there, right? So we've spoken about Bezier, Topcat, yeah, with Simbad, and this CDS, right? So then there is a host of statistical packages. Whenever you deal with data, it is very essential that the results which you get, you have to back it up with statistics. Without a proper statistical backup, your data or your results are not accepted. By just looking at a few objects, suppose you have studied 5 objects and you are saying that this is the trend, it is whether it's sufficient or not, or how significant it is, at what level of significance you have, it has to be done. So there are a variety of statistical packages. There are certain ones which are proprietary ones which you have to buy, like SPSS. It's a very commonly used one mostly by social science and life science people. You have the Statistica, you have Maple, MATLAB, Mathematica. So these MATLAB, Mathematica, they don't only do statistics, but they do much more of mathematics, right? But these, you have to buy them. They cost money and cost quite a lot of money. Then you have these public domain ones like BrightStar, CS Pro, Minuit, and so on. And then there are certain which are the open source ones. So the open source ones are the ones where even the source code is distributed with you. So public domain ones are also free to use, freely distribute, but open source ones are free to use, free to distribute, and it comes with a source code also. So you can even make changes to those things to alter it to your liking or this thing. So we have PSPP, a free software, which is the replacement for this SPSS. We have R. Again, a very good tool, very sophisticated statistical package. Um, uh, we can have sessions on this. If not in this program, we can meet on weekends if there's a large enough group, and we can show how to use R. We have SimFit, SOFA statistics, statistical labs, and so on, right? So instead of thinking of all of this, I would suggest just think of using R, or rather use Python, which is now becoming very popular, and it is replacing, it is attracting all people from SPSS and uh, from all people who have been using it for a long time. They are all being attracted to Python because it's an extremely versatile one where you can program in it. You have excellent image uh, reduction facilities and so on uh, and so on. Okay. So statistical tools for astronomers in public domain, like I said, R is an extremely good one. And there was one VO tools, virtual observatory tools, in which we had VO tables, which allows you to display tables and do some analysis of that. VO plot, which goes with it, which can do plots, scatter plots, histograms, various things. You have Topcat, Mirage. So for some reason, VO plot and all are now slightly going out of fashion and out of interest. The Topcat and Python are becoming very, very popular. So in these sessions tomorrow, so we'll be working much with Topcat because it's very simple to use and very good one. And it runs on. In fact, all these things run on all machines, Windows or Linux or Mac or so. Then we'll be looking at this Aladdin. And then we have this for spectrum display analysis. We have BioSpec and SpecView, right? So this when virtual observatories were getting started, there were different countries, different people got together, and they were building these tools. And these are still available, and I'll show you where you can get them from. But some of them are still in the beta version because other tools have really grown in time and people have they have migrated to them. Right? So here's a slide on R. It's a free software environment for statistical computing and graphics. It compiles and runs on a variety of Unix platforms on Windows and Mac OS. It's from the GNU project, and it is similar to the S language, right? So it is a precursor to the S language. S was for statistics, and since it was an enhancement, it decided calling R. And it was first developed in Bell Laboratories, formerly AT&T, and so on. So we can have a look at R as well as we proceed. Yeah, and we have this VOstat, and this is how it goes. This is what it looks like. You go to the site and look at VOstat. You specify the URL from where you get the data, and or you can choose a data file which is residing on your system. So you have both options. You can use a URL, or you can use it from your local machine. You load the table, and then you get a panel of this kind which says you want descriptive statistics or multivariate analysis, or you would like to do statistical tests or exploratory tools. So when you curve fitting, and when you click that, it does whatever you wish to do, right? So yeah, so this is how. So for example, I say scatter plot, and I say what against what. It gives you a plot, and You can do it in polar coordinates or projection. Yeah, you can see here. You can see what kind of projection you need, what are the standards, what are the. So it's very easy to use. And on the right hand side again, you can see you can convert the axis to log scale or whichever. So just by clicking these buttons, you can do that. You don't have to do anything of code writing or and so on, right? So you can get all these kind of things, histogram, bar plots, scatter plots, and just by clicking around. And you can see, go to the site and says download your cat beta version zip. You download it and install it. Okay. So I'll just show you how it's done. Yeah, so we will do some, yeah. So let me stop with this and start the browser. Okay. So what I would suggest is, so our best bet is Google. You go there and look for Top Cat. And Top Cat, there's a Top Cat cartoons also. So just to make it clear, say astronomy, oh, even if it's badly. And here you have Top Cat astronomy. And you can download Top Cat from So these are yeah. Bobcat download. This way to download Bobcat. Yeah. So Bobcat download, and you can download it. Download for Windows, yeah, for example, and it would download it. And when you run it, similarly for so your work for today is on your systems, which you should come with for tomorrow. Download the Stopcat and share. I share the screen. Not this whole thing.
You want to share the
Advancement of portion with
no.
yeah. Okay, so yeah, I'm sharing this portion of the screen, and you see there is this Stopcat. Good. So for them probably from others. So you have this Stopcat, and you need to install Java, and from here you can say open, specify what kind of format it is, the file, go to the location where the file is. So for example, I say comma separated variable, and I go to the file browser, and on my desktop I have this thing, and I specify is in what format, comma separated, and say OK. Yeah, so the table is loaded, and this is the table, right? And if I want to say plot the first two yeah, so I specify here which one, the x-axis is what and y-axis is what, and I've taken RA and dec, and here this is scatter plot, this is plot, right? So it is as simple as that. So similarly, we can take sections of it and do various kind of things, and we shall do that in the next session. In the same way, you look for Aladdin and work on that. There's no more time. Yeah. So with this, let me end. Similarly, VO tools you can search on net, and we have VO tools also kept here. Tomorrow I will